Hey everyone, welcome to our first video lesson in our unit on energy. In this video, we will be talking about what energy is, the different forms that energy can take, and for a couple of those types of energy, we'll get into how to go about quantifying, how to calculate the amount of energy that an object has. So let's go ahead and dive in. So first of all, what even is energy? Energy is one of those things, kind of like momentum, where we have an intuitive sense of what energy is. We can recognize it when we see it, but it's hard to put into words, I think in part because energy can take so many different forms. It can look and sound and feel like so many different things depending on what type of energy it's manifesting as. So it's hard to define succinctly. We'll go with the definition of energy is the ability to cause change in the environment in some way. All right. We measure energy in a unit called joules, which can be abbreviated with a capital J. And to give you a sense of what 1 joule of energy is, if you imagine having a 1 pound object 9 inches off the floor and dropping it, that object will lose 1 joule of energy in the process of going from 9 inches off the floor to then hitting the floor. Okay, or you could think of it as the amount of energy it takes to lift that 1 pound object about 9 inches off the floor. Okay, just to give you a general idea of about how much energy a joule is. And then last thing I want to mention just to start here is that energy is a scalar quantity. So what's the significance of that? That energy is a scalar and not a vector. This tells us that energy does not have direction. All right, when we think about something having energy, it doesn't necessarily have energy to the left or energy down or something like that. It just has energy. And so for our purposes then, as we are calculating energy, we do not need to be worrying about direction. So if we're trying to quantify the amount of kinetic energy something has based on its motion, we don't have to worry about whether it's moving in the positive or negative direction. We calculate the energy the same because it's a scalar. We're not worried about direction for energy. All right, so then let's start diving into some of those different ways that energy can manifest, the different types of energy. So in general, we can take all types of energy and place them into one of 2 different categories. One category of energy is energy that reflects the motion of an object or a particle, that it has energy because it is moving more rapidly, more dramatically, but it requires motion that's inherent in that type of energy. Our other category of energy is stored energy, which we call potential energy. And that energy is stored based on the relative position of an object or a particle. Okay, it has something to do with where it's located that allows it to store up some of this potential energy. And so when we think about the term potential energy, you can kind of think of it as this object or this particle is located in a position where it has the potential to move, that we've given it some energy that could be converted into motion. The object isn't necessarily moving yet, but it's somewhere where it could start moving. I get that that's still a little hand-wavy. We're going to come back to that and look at some examples to hopefully help clarify that a bit. Okay, so let's go through some of these different types of energies based on whether they're motion-based or potential energies. So let's start with the motion-based because those, I think, tend to be a little bit more concrete because we can actually like visualize motion, see motion, things like that. First motion-based energy that is usually the first one that springs to mind for people is kinetic energy, and that's the energy of moving macroscopic objects. All right, so if we think about the energy that a speeding car has, or a running cat, or a spinning merry-go-round, something you can see moving, that's kinetic energy in action that we're seeing. Okay, so that's one type of motion-based energy, but then if we start to scale down a little bit, we can start thinking about some other energies associated with the motion of itty-bitty particles, okay? So for example then, thermal energy would be another motion-based energy, because when we think about something having thermal energy, if something is hot, right? What that really means is that the molecules or atoms making up that object are moving faster. The faster they're moving, the hotter the object is. So at the end of the day then, thermal energy is a motion-based energy because it reflects the motion of the particles. The faster they're moving, the more thermal energy and the higher the temperature of that object. Okay, so if we think about an oven, steam engine, anything that operates by changing temperature, we're really looking at then an object that's using thermal energy. Okay. Another example of a motion-based energy where we really have to think about the motion of itty-bitty particles would be electrical energy. If we think about what an electrical current is, when you plug something into an outlet, what's really happening is you are getting energy by getting charged particles to move. Typically that's electrons, sometimes that's ions, but in any case we're talking about some particle with an electric charge moving, and the more it's moving, the more rapidly we're getting charges moving, the more electrical energy an object has. So if we think about a phone charger, lightning, anything that plugs into a wall or operates on batteries, which is chemical energy at its core, but produces electrical energy. That would be an illustration of this particular concept there. Okay, a couple more types of motion-based energies for us. Sound energy is another motion-based energy because at the end of the day, sound is really all about vibrations. Okay, for you to be able to hear me speaking right now, what's happening is my voice is vibrating the air particles, which bump into other air particles, which keeps them vibrating, moving until they reach the air particles near your ear, and then that vibrates your eardrum, and so on and so forth through the anatomy of your ear, and then your brain is able to process those vibrations and make sense of all of it. Which is kind of wild that all of this stuff is happening just super, super quickly without us even having to think about it. But you know, I'll save that geeking out for another day. All right. But sound energy is ultimately about getting particles to vibrate. And so since it's all about those vibrations, sound energy is another motion-based energy that we get from talking, music, clapping, a lot of things. All right. Last motion-based energy for us to talk about for right now is light energy. All right, and we're going to spend a lot more time talking about light and what it is and what's moving, really, when we're talking about light propagating. But ultimately, much like sound energy, light energy derives from the movement of waves, and in this case, electromagnetic waves, or we can think of them as photons. And again, we're going to get into all of that in much more depth later in the semester. All right, but ultimately, for light to propagate, something has to be moving. Okay, so we talk about whether we're talking about light bulbs, sun rays, whatever, it's all motion-based. Okay, so those 5 types of energy then all derive from the motion of objects or the motion of particles or waves in some way. All right, so let's jump over then to potential energies, these stored energies that don't require motion, but that could be translated into motion under the right circumstances. Okay. So first potential energy for us to talk about is gravitational potential energy. All right, gravitational potential energy is the type of energy that an object has when it's in a position where gravity can accelerate it and get it to start moving. Okay, so if we're talking about like in the earth, right, or not in the earth, on the earth, if I take this pencil and I lift it up, right, the higher it goes, the more opportunity there is really for gravity to accelerate it and get it going faster and faster and faster. If I drop it from a low height, it doesn't end up getting very, very fast before it hits the ground. But if I raise it up higher, it's going to have more time to accelerate, and it's going to be going faster and have more kinetic energy down by the bottom of its journey. Okay, which means that as I raise up this pencil, I'm giving it more and more gravitational potential energy. Okay, so we can think of gravitational potential energy here on Earth as being a reflection ultimately of an object's height above the Earth's surface, right? It's based on its position. This object isn't moving, but it still has that potential energy because it has the potential to move if I were to let it go. Okay, and just to get us sort of primed for thinking about fields a little later in this unit, I can also think then of this as being energy that's stored based on this object's position within Earth's gravitational field. around it. Okay, so it's all about that position in there. So if I think about a seesaw or a skydiver or roller coasters or things like that, all of those are making use of gravitational potential energy. We see at the top you're not necessarily moving, but you're in a position where gravity can get you to start moving pretty rapidly as a result. Okay, so that's one type of potential energy. Another type of potential energy is elastic potential energy, which is based on an object getting stretched or compressed, deforming the object in such a way that it's going to snap back and translate then that stored energy into motion as it returns to its default state. Okay, so if I think about a spring, stretching a spring or compressing a string, or a spring, excuse me, a slingshot, rubber band, those sorts of things all make use of elastic potential energy, where if I stretch them out, they're not moving, but as soon as I let them go, they will start moving. So I'm storing energy in them. Another type of potential energy, if we start to then zoom way, way down here, would be chemical energy, which is ultimately energy that's stored in these chemical bonds between atoms, holding them together to form molecules. So if I think about things like gasoline, food, stuff that undergoes chemical reactions in order to produce usable energy, those make use of chemical energy. Right? And then if I zoom down even more, down inside the atom, I can get to nuclear energy, which is stored in atomic nuclei, holding those protons and neutrons together. And so this is the energy that we're able to release through the process of either nuclear fusion or nuclear fission. So if we think about nuclear bombs or what's going on in the sun to be able to produce so much energy, those are nuclear processes making use of nuclear energy. And again, we'll get more into that a little bit later as we dive into astronomy. So those are a few different examples then of what we're talking about when we're talking about potential energies. They don't necessarily immediately mean motion, right? An object can be still but still have potential energy, but the positioning of an object or a particle is such that we could get energy released from that interaction, right? So then another way I want us to be thinking about categorizing energy has to do with mechanical energy. So I mentioned previously that the first half of physics is all about mechanics, which has to do with looking at motion at a macroscopic level, and then non-mechanical physics has to do with more things at the microscopic level, at other scales then. So then we can also then think of energy in these different categories as well. So if we think about mechanical forms of energy, those are energies that focus on macroscopic objects that have to do with the motion or the position of objects that we can actually see with our own eyes. The non-mechanical energy would be forms of energy that are deriving from the motion or position of teeny particles that we're not able to see. So then my question to you is, now that we've looked at all these different forms of energy, which ones would be classified as mechanical? Hint, there's 3 that we've talked about so far. All right. So then our 3 types of mechanical energy are kinetic energy, because kinetic energy is about the motion of large objects, right? Gravitational potential energy, and elastic potential energy. All of our other forms of energy are really looking at things down at the level of particles, atoms, molecules, subatomic particles, itty-bitty things, but these 3 we're able to really see with our own eyes in action, okay? And for our purposes in this class, we're going to focus in on kinetic and gravitational potential energy. We're not going to focus a lot on elastic potential energy, but if you take AP Physics 1, there's all sorts of elastic goodness in your future, okay? But for now, we're going to focus in on those first 2, all right? So let's then start thinking about how we can go about quantifying these forms of mechanical energy, the kinetic and the gravitational potential energy. And we looked a little bit already in our lab at gravitational potential energy. What were some of the factors that we identified in our lab in our previous class that might affect the amount of gravitational potential energy that an object has? So in our lab, we really saw sort of 2 big things. We saw that mass influences the amount of potential energy an object has. The more mass it has, the more energy it's going to have. And we saw that height influences gravitational potential energy. The higher up it is, the more potential energy it has. Okay, and so ultimately then our equation for gravitational potential energy ends up being that gravitational potential energy is equal to the mass of the object multiplied by the pull of gravity, that gravitational acceleration, which here on Earth is 9.8 meters per second squared. But if you were to move to a different planet or the moon or something like that, there would be a different amount of energy that's stored up in that gravitational field based on how strong that field is. And again, we're going to dive more into that a little bit later. And then we multiply, so mass times gravitational acceleration times the height above our reference level. And when I say height above reference level, it just means you kind of get to choose your 0 point for where you're measuring height from. So if I'm lifting up this pencil here, I could measure the height above my desk, or I could measure the height above the floor. Either of those would be perfectly good ways to think about potential energy, as long as I'm consistent throughout the problem with what I define to be my 0 point. Okay, because ultimately when it comes to potential energy, we're less interested in like an exact number and more interested in changes in potential energy. How much did our potential energy change? How much got turned into kinetic energy? Things like that. Okay, so usually the floor is a good reference point, but if it makes sense to use something else as your 0 point for height, you can do that as long as you're consistent. Okay, so again, gravitational potential energy in joules is equal to mass in kilograms multiplied by acceleration due to gravity. Here on Earth, that's 9.8 meters per second squared, times the height of the object measured in meters. So that's gravitational potential energy. What about kinetic energy? What might be some factors that would influence kinetic energy? And here's a hint. There are two factors that influence kinetic energy. Ultimately, our two big factors that influence kinetic energy are mass again. Mass shows up again here because the more massive an object is, the more ability it has to cause change, right? There's a big difference between dropping an apple on your head and dropping like a freight train on your head. So mass plays a role in this, and then speed. The faster an object is moving, the more kinetic energy it's going to have. And so we see both of those showing up in our formula for kinetic energy. Kinetic energy is equal to 1/2 times mass in kilograms times speed squared. All right. And again, here we're using V to represent speed rather than velocity because energy is a scalar. And so we're not worried about direction. So we can use the scalar form of velocity, which is speed. All right. Please note that when we've got that squared on our speed, only the speed is getting squared. Okay, so please do not go squaring mass. Don't square the 1/2. It's just speed gets squared, and then you multiply that by 1/2 and by the mass. All right, and so we've got our equation then for kinetic energy, 1/2 mv squared. We've got our equation for gravitational potential energy, that's mgh. And so then, for our purposes, the mechanical energy of an object, the total, all the different types of mechanical energy, is just equal to kinetic energy plus gravitational potential energy. Again, if we were dealing with elastic potential energy, that would pop up in here as well. But we're not going to worry about that. So it's just going to be these two for our purposes right now. Let's go ahead and do a little check for understanding then to wrap us up. So in this problem, post-COVID world, everything is good, humanity is saved, you're having a family gathering and a feast together. So your grandma is pulling that turkey out of the oven to feed everyone, but alas, there is a hole in her oven mitt, and so she gets burned, and reflexively she just automatically just like chucks the turkey off. It's a big old turkey. It's 10 kilograms. It's like 22 pounds. So, you know, it's a big family gathering apparently. The turkey as a result is now moving at 2 meters per second at a height of 2.5 meters above the floor. And then it hits your dad in the face. So, you know. Fun. All right. Two questions for us to figure out. First of all, let's calculate what the mechanical energy, total mechanical energy of the turkey is right before it collides with your dad's face. And then secondly, what are some of those non-mechanical forms of energy that the turkey either has or produces during the collision? Okay, so starting with that mechanical energy, in order to calculate this out, let's go ahead and use our guess method. We'll list out our given information, identify our unknowns, find some equations to help us, substitute some values in, solve it through, make sure it makes sense. All right, so the mass of our turkey we know is 10 kilograms. Other information we know is that it is moving at a speed of 2 meters per second and at a height of 2.5 meters above our reference point. All right. This is presumably happening on Earth. I don't anticipate any like Martian family gatherings. Okay, so we're going with a gravitational acceleration of 9.8 meters per second squared. And we're trying to calculate, our unknown is the mechanical energy. All right, so if we want to calculate mechanical energy, that's equal to kinetic energy plus gravitational potential energy. Those are our two major forms of mechanical energy that we're focusing on here. So if I can calculate each of those, if I can calculate kinetic energy and I can calculate potential energy, I'll just add those together to get the total mechanical energy. All right, so starting with kinetic energy, my equation for kinetic energy is 1/2 times mass times speed squared. And I know mass and I know speed, so I can just plug and chug, baby. All right, so that's going to be 1/2 times 10 kilograms times 2 meters per second, and that 2 gets squared because our speed is getting squared. So 1/2 times 10 times 2 times 2. All right, so 1/2 times 10, that's 5, multiplied by 2 squared. 2 squared is 4, so 5 times 4 is 20 joules of kinetic energy in that turkey. Then let's move over to the potential energy, the gravitational potential energy of our turkey. Gravitational potential energy is equal to mass times gravitational acceleration times height. I know all of those from the information given to me. So the mass is 10 kilograms, gravitational acceleration is 9.8 meters per second squared, height is 2.5 meters. I go ahead and multiply all of those together to get a total potential energy then of 245 joules. It's a lot of potential energy there in my turkey. And so then to find the total mechanical energy, I'm just going to add those two together to get a total of 265 joules of mechanical energy that the turkey has. All right. Second question then is, what are some of those other forms of non-mechanical energy that we see in the turkey during that collision? All right. There are a bunch. Depending on kind of how detailed we want to go in here. Maybe one of the more obvious ones is thermal energy, right? The turkey was just in the oven. It's pretty darn hot, so it's definitely got a decent amount of thermal energy contained within it, right? I would imagine that that when it hits your dad in the face, there's going to be some sound energy that's produced because there's going to be like a nice little splatting sound, just to get everyone, you know, nice and in the mood to eat. And then, given that this is turkey and it's food, we could also then be thinking about the fact that, you know, the turkey has chemical energy, and if we still eat it after it's collided with dad's face, then that's going to be usable energy that our bodies can make use of. All right, so the turkey has chemical energy in it as well. Technically, there is also nuclear energy in the nuclei of the atoms that make up the turkey, as well as some electrical energy if we're looking at the movement of the electrons in there. But they're not super relevant here. We're not really making use of those forms of energy either during the collision or in the process of eating the turkey. So they're there, but if you didn't focus on those, I think that's completely okay. All right, so that's it for our introduction to types of energy and some of those mechanical forms of energy in particular. I hope that clarifies a bit what we're talking about and how you can start to recognize energy around you.